Okay, so just today we'll discuss more on the matrix of a linear map. Okay, so the setup here is let V and W be finite dimensional vector spaces. And throughout, we're going to fix a basis for each one. So we'll suppose that V has basis V1 through Vn, and W has basis W1 through Wm. Okay, so these are finite dimensional vector spaces with fixed bases, but they don't necessarily need to be the same dimension as each other. Okay, now we know that one thing that we saw was that any linear map T from V to W is determined entirely by where it sends the basis vectors. Right, because we said you can send the basis vectors anywhere, and there's a unique linear map that sends the basis vectors to the place that you chose. So in order to determine what a linear map does, you just need to know what it does to a basis. Then it's forced, what it does on the rest of the space is forced. Okay, further, since BW is a basis of W, for each of these TVIs, we can write them as a linear combination of the W's. We can write each TVI, and it's unique because they're a basis, uniquely as a linear combination of the W's. So if we just record that information, right, how to write the TVI as a linear combination of the W's, that should contain all the information about T. And that's the information that we put in a matrix to encode the data of the linear transformation T. So, right, how many numbers will we need? Well, we need to know about n vectors, TV1 through TVn, but each of them is written as a linear combination of the W's, and there are m W's, right? So there's n of these and there's m of these. So we'll need to keep track of m times n pieces of information. Okay. So we make the following definition: an MbyN matrix A is just a rectangular array of elements of F, the field, the scalar field, with m rows and n columns. Okay, so in mathematics, if there's ever something that depends on rows and columns, the number of the rows almost always comes first. Right? So a 2x3 matrix has 2 rows and 3 columns. Okay, so sometimes it's useful to be able to identify which entry of the matrix we're talking about. So we use a numbering scheme that again puts the rows first and the column second. So this entry is in the first row in the first column, so it's A11. The next entry is in the first row in the second column, it's A12. This goes all the way to A1n because there's n columns. This goes down to AM1. This goes down to AMN. Right? So we're keeping track of m times n scalars. So i.e., sometimes we'll use the notation AJK. This is the entry in the jth row and kth column. Okay, and basically what we'll do, the way that we're going to set this up, is each column is going to contain the data for one of these TVIs, right? There's n columns. And each of these columns consists of m scalars. These m scalars are going to be the scalars that you need to write the TVI in terms of the WJs. Right, so that's how we're going to store the m times n pieces of information. Okay, I should note that, of course, these scalars depend upon the choice of basis that you make, right? If you choose a different basis here, then some of these vectors are different, and so you get different vectors. And if you choose a different basis here, then you rewrite, what scalars you need to take for the basis vectors to get the vector you want. That's different. So when we record a matrix, implicitly we're making some choice of basis. Okay, so let me just define this really clearly. Right, so suppose that T is a linear map from B to W, and we're going to retain some fixed choice of basis for each of V and W, and retain the bases BV and BW above. Okay, then to each linear map, we associate a matrix, the matrix of T, with respect to these bases. Okay, so like I said, the numbers that you get, the scalars that you get depend on your choice of basis. So anytime you say, oh, the matrix of a linear map, there's some implicit choice of basis. So when you want to make it clear, you say, here's the matrix with respect to this basis. Okay, but the matrix of T is the MbyN matrix. So we'll say script M of T. Right, so this means the matrix that you get from T, but whose entries AJK satisfy T of VK equal A1K W1 plus AMK WM. Okay, this is here. All I'm doing is I'm just rewriting this process that I said I would do over here. Each column represents one of the TVIs. The entries in the column tell you what linear combination of the W's to take. That's exactly what I'm saying in this definition. Okay. So in other words, the kth column of this matrix of T records the coefficients for writing TVK as a linear combination of the W's. That's really what we're doing. Okay, so one thing that you'll notice about this notation is here, this definition is the matrix of T with respect to a basis, but this notation doesn't anywhere mention what the basis is. Okay, so if the basis is not clear, or if the bases rather are not clear from context, right? So you want to be very clear, then you should say M, I can talk about the matrix of this linear map with respect to this basis for V and this basis for W. Okay, so really, in order to define this thing, you should give the linear map and the two bases, but a lot of the time we'll be working with some fixed basis of the vector space, of each vector space. And if you have some fixed basis of each vector space, then you don't need to mention which basis you're using because we all agree. Right, so generally, if no bases are given, right, so no one tells you what the bases are, and T is a linear transformation from Fn to Fm, what we do is we just use the standard bases. Okay, so like in Math 308, when you learn about matrices as linear transformations from Rn to Rm, every matrix that you wrote was with respect to the standard basis. However, matrices are more flexible than that. You can write matrices with respect to any choice of bases that you want. Okay, so let me give you a very concrete example, just from like the kind of thing you might see in Math 308. So let's suppose that we have a linear transformation from F3 to F2, defined by T, what it does to a vector x, y, z, it just spits out the vector, let's say 3x minus y, 2x plus 2z. Okay. Now, if you want to find the matrix of T, what do? Well, you need to take a basis for this space, and then you need to write I mean, you need to plug it into T, and you need to write the result with respect to the basis of this space. But here, no basis is given. That must mean I mean the standard basis, right? So the standard basis here is E1, E2, E3. So we just need to know TE1, TE2, and TE3. What is TE1? That's T of 1, 0, 0. So that's 3, 2. T of E2, that's 0. You plug in 0, 1, 0. So you get negative 1, 0. If you plug in 0, 0, 1, you get 0, 2. Okay, and notice I've written these outputs really with respect to the standard basis on F2. Right? This is what this notation means. So the matrix of T, each column should record one of these vectors, should just record the coefficients, 3, 2, negative 1, 0, 0, 2. Okay, so this is really what you were doing in 308. But as you can see, whenever you wrote down a matrix like this, or almost every time you wrote down a matrix like this, you were using the standard basis. We can be a bit more flexible and allow other bases. Right? Also, we're talking about general abstract vector spaces in this course, where you might not necessarily have a standard basis that's the one that you recognize. Okay, so one thing that you learned in Math 308 is that there's a correspondence between MbyN matrices and linear transformations from Fn to Fm. So in Math 308, you learned that if you have a linear transformation from Fn to Fm, T, then you can associate to this a certain matrix, an MbyN matrix. And similarly, if you have an MbyN matrix, you can go back, right? You can define a linear transformation from Fn to Fm from using that matrix. Okay, so the only extra wrinkle, really, like I said before, is that we're not just talking about these vector spaces. We're talking about any finite dimensional vector space. And then also, so here, what we're going to do is we'll allow any finite dimensional vector space. And on this side, we'll allow any basis, right? So any bases for these finite dimensional vector spaces, which means that we need to record this somehow. Okay. So again, think about this correspondence, right? Somehow there's some relationship, which we don't fully understand yet, between linear maps and matrices. Okay, so here I'm being deliberately vague because we haven't studied this yet. But you know here that if you have two linear maps, we learned that you can add them. So you have an addition, and you can scalar multiply them. You have scalar multiplication if you have a linear map. Similarly, if you have two matrices of the same size, you can add them, you can scalar multiply them. One question is, in this correspondence between linear maps and matrices, do these things also correspond? In other words, so suppose that S and T are two linear maps from V to W. Well, we just saw the process where you can get a matrix of S and a matrix of T once you've fixed a basis, right? So fixed bases. Here, you can get a matrix for S with respect to this basis and a matrix for T with respect to this basis, right? And these are both MbyN matrices. Well, here you can add the linear maps. You get a new linear map. Here you can add the matrices. You get a new matrix. Another thing you can do is you take this linear map and then you map it over here. You get M of S plus T. And you could ask, how are these two things related? Right? Adding the linear maps and taking the matrix, or taking each matrix and then adding the matrices together. Okay, but this is linear algebra, which means that to any question you have, the answer is the nicest possible answer. So let me just tell you the result. So if you have, okay, again, throughout today, V and W are both finite dimensional vector spaces with some fixed choice of basis. So if you have two of these, if you add the linear maps and then you take the matrix you associate to that, that's the same thing as taking the matrix of S, the matrix of T, and adding it. Okay, so this says that the addition of linear maps corresponds to the addition of matrices. Okay, similarly, sorry, I only need one here. So suppose I have one linear map and one scalar. Then you could scale the linear map and then take its matrix. Or you could take the matrix of T and then scale and multiply the matrix by lambda. And what you get is the same result. Okay, so scalar multiplication also corresponds between these two spaces. Okay, so I won't prove this. This is really just kind of an exercise in writing down and understanding this definition, essentially, this definition of how to associate a matrix to a linear transformation. So you should do it, but somehow I think maybe watching me do it is not going to be any more instructive than you reading the textbook. You really need to write down and go through it. Okay. Another thing that we saw was that the set of linear maps, these formed a vector space. Okay, I said it's not obvious, but can be checked that this set, which has an addition and a scalar multiplication, also has the structure of a vector space. You can also ask, well, I can add two matrices of the same size. I can scalar multiply them. So I have an addition and a scalar multiplication. Does this make the set of all MbyN matrices into a vector space? And the answer is yes. And to be honest, it's not that hard to check, right? You need to check that addition is associative, addition is commutative, there's additive inverses, there's a zero element, which is a zero matrix, scalar multiplication distributes over matrix addition. All these things are sort of routine checks because the definition of addition is just point-wise, entry-wise for a matrix. Okay, so I'll just define. So for positive integers m and n, the set of all MbyN matrices with entries in F is a vector space with the addition and scalar multiplication we're used to. And it's denoted in your book F of m comma n. Okay, but also sometimes this is denoted F of m times n, sometimes. Okay, also you might see this as m by n f at some point. Okay, but I'm going to stick with your book's notation for as much clarity as possible. This is the notation I use for the set of all possible MbyN matrices. Okay, and this vector space has dimension m times n. Okay, so you can check this because I can give you a basis. Okay, so let me just give you an example of, say, 2 by 3 matrices. Right, so a basis of F23 is given by the so-called elementary matrices. So what you do is you just stick a 1 in one spot and zeros everywhere else. Okay, these are called elementary matrices sometimes. That's sort of an overload term. Let me not say that, but you can check that these are linearly independent and they also clearly span. You can get any matrix, any 2x3 matrix as a linear combination of these things. So these things are a basis. Therefore, this thing has dimension 6. You just multiply the number of rows times the number of columns. Okay, so I haven't really checked anything here, but you should be able to check all these things. Okay. But remember, okay, right? So this was a vector space. I also didn't check that. I should mention, but I said that you could check it. Now this is a vector space, but we said that actually this has even more structure, right? Because if you take something in this vector space and you take something in this vector space, something in this vector space, something in this vector space, and I guess I want to take t from here, s from here. These are two vectors living in two different vector spaces, but because they're functions, you can compose them. So you get st, which lives in a different vector space. Okay, well, if you fix bases for u, v, and w, then this is the linear map side. What about the matrix side? Well, you can take the matrix of t. You can take the matrix. Okay, I guess I need to tell you what sizes, what dimensions these things are. So let's say, how do I want to set this up? Let's say that the dimension of v is n, that was from before. Dimension of w is m, and the dimension of u is p. And we have some fixed bases for these. Okay, now t goes from u to v. Ah, gosh. Okay. Sorry, I want to set this up so that the notation is the same. Oh, actually, maybe I am setting this up so that this notation is the same as your book. Yeah, okay. This should be fine. Okay, so t goes from a p-dimensional vector space to an n-dimensional vector space. So this is an f of n comma p. S goes from an n-dimensional vector space to an m-dimensional vector space. So this one is in f of m comma n. And the composition st, this is a matrix. I mean, this thing goes from p-dimensional to n-dimensional. Sorry, p-dimensional to m-dimensional. So this is in something, it's an m by p matrix. Okay, so here I have 3 different matrices, potentially all of different sizes if m, n, and p aren't all the same. So the question is, how are these matrices related? How is this matrix and this matrix related to this matrix? Well, what we're going to do is we're going to define a matrix multiplication such that when you multiply the matrices for S and the matrices for T, you get the matrix of ST. Okay, so this matrix multiplication will only be defined on matrices of a certain size, right? So this number needs to match this number because the domain of S needs to match the codomain of T. Okay. The way to remember this mnemonic is S is an m by n matrix, T is an n by p matrix. So these two numbers need to match, and the resulting matrix is an m by p matrix. Okay, so what we're about to do is we're about to define a matrix multiplication on an m by n and an n by p matrix. The way that we're just going to rig it, we're going to rig the definition so that when you multiply the two matrices, it's the same thing as composing the functions. So here's this rigged definition. This is rigged. Okay, so let A be an M by N matrix and C be an N by P matrix. Then the product A times C is defined to be the M by P matrix whose jkth entry is given by, okay, so the jkth entry of this product is you sum from R equals 1 to N of A, J, R, C, R, K. Okay, so what are you doing? If you want to know the entry, say in the first row in the second column, what do? You look at all of the A1Rs and all of the CR2s, and you add them up, right? This is just an example if you want the 1-2 entry. So what are you doing? Here, you're fixing the first row of A, and you're going along every entry in that row. Here, you're fixing the second column of C, and you're going along every entry in that column. And you're multiplying them one at a time, and you're adding them all together. Right, so this thing is the dot product of the jth row of A and the kth column of C. Okay, which is the definition for matrix multiplication that you should remember from, I don't know, 308, right? So you take two matrices like this. How do you compute the resulting matrix? The first thing you do is you take the first row and you dot it with the first column. That gives you the entry in the 1-1 spot, right? So that's 2. Then you take the first row, you dot it with the second column. You get 2 minus 2, that's 0. Second row, dot it with the first column, 3. Second row, dot it with the second column, I think 4. Okay, so this is just the matrix multiplication that you sort of already know. And again, in order for this process to make sense, the number of columns, right? There's 3 columns here, 3 rows here. The number of columns of A needs to match the number of rows of C. Okay, so this definition is rigged to make the following proposition true. So let T be a map from U to V, S be a map from B to W, be linear maps, and fixed bases U1 up through UP of U, V1 up through Vn of V, W1 up through Wm of W. Then with respect to these bases, multiplying the matrices for S and T gives you the matrix of the composition ST. Okay, so let me just sketch the proof. Okay, the proof is really just a computation where you have to be really careful with the indices and knowing what you're doing. Okay, so right, I mean, the definition of matrix multiplication is kind of weird. Sort of hard to remember like what the formula is for it. But of course, the proof has to use it, right? Because the proof is about matrix multiplication. So if we let A be the matrix of S and C be the matrix of T, I want to understand the matrix of ST. Okay, well, how do you get the matrix of ST? You need to take, right, ST is a map from U to W. You need to take a basis of U, I mean, this given basis of U. You need to plug it into ST, And you need to write the result as a linear combination of the w's. Right? So you need to know st of uk for every k. So what is st of uk? Well, st of uk, that's s of t uk. Okay, well, what is t of uk? Well, t of uk is the kth column of C, right? Because C is the matrix that recorded what T does to the basis of U. Right? I mean, you get the information from the kth column of C. What we'll do is we'll sum from R equals 1 to N. This is the kth column of C, written with respect to the basis of the V's. Okay, so this is exactly what TUK is, because C encodes what TUK is. Okay, well, now this is a sum, and S is linear, which means that I can push it through the sum, and I can also pull out scalars, right? So since S is linear, this is a sum R equals 1 to N, CRK of S of VR. Okay, well, what is S of VR? You get this data from the rth column of A, right? A is the matrix for S. A tells you exactly what S does to the basis of V in terms of the basis of W. Right, so this whole thing becomes, whoops, sum R equals 1 to N, CRK. Now S of VR is going to be a sum J equals 1 to M of the rth column of A in terms of the basis vectors of W. Okay, but now I can re-index the sum. I mean, I could J equals 1 to M, R equals 1 to N, and let me just, these A's and these C's are scalars, so they commute. Wj. So this should record the data of how to write UK in terms of the W's. So these guys should be the entries of the matrix for ST. Right? This should be the kth column. So in kth column. Right? But notice that this is how we defined matrix multiplication. These are the entries of the matrix AC. It's exactly the same thing as this. And so since that's the way that we define it, this shows that AC is just the matrix of the composition ST. Okay, so there's nothing super deep going on here. But even though it's not super deep, it is kind of technical, right? Okay. So, the most important thing is that you know how to actually multiply two matrices if you're given some actual numbers. However, there are some things that you will need to prove about matrices where you actually need to be able to write down like the formula in the abstract. So when you need to do that, you should figure out how to do it. Okay. So I still have a little bit of time. Yeah, at least 5 to 10 minutes. So let me start talking about invertibility and isomorphic vector spaces, which is what we'll continue with on next Monday. Okay, so first, just the definition of invertible. Okay, so a linear map T, if you have a linear map from B to W, you call this map invertible if it has an inverse, basically. What is the inverse? An inverse is like a map that should undo what T does. Right? So if there exists a linear map S going from W to V, such that if you first do S and then you do T, you get the identity. If you first do, sorry, this one is first do T, then do S, you get the identity. Or if you first do S and then do T, you get the identity. Okay, notice though that these are two different identity functions, right? ST goes from V to W to V, right? First you do T, then you do S. So this is the identity on B. TS, on the other hand, means you first do S and then you do T. So this composition is the identity on W. So if you can find a map that undoes what T does, if you do it first or if you do it second, that's called, then you say that T is invertible, and you call S the inverse of T. Okay, but right now I can only say call it uninverse of T, because I don't know, maybe you could have more than one, right? If you could have more than one, then I shouldn't use the word the, because if I said the inverse, you could say, which one do you mean? So again, this is one of these things. It's not obvious just from the definition that an inverse should be unique. Okay, how do I know that if I have a linear map T, it's not possible to have two different linear maps that satisfy this property of undoing T? But it is true, in which case we can change it to B. So here's the proposition: an invertible map has a unique inverse. Okay, so anytime you want to prove that something is unique, a good strategy is to suppose you have two of the thing, and then show that actually those two things that you thought you had were actually the same thing. Okay, and I mean, the proof isn't difficult, because it very much mirrors some of the stuff you did in 300, or if you did in the first week of this class. So suppose that you have a linear map that is invertible, and suppose that S1 and S2 are both inverses. Okay, so I want to understand, or I want to show that S1 equals S2. But what you do is you just consider S1 T S2. If you consider this map, well, function composition is associative, so you can associate it in either way. If you associate it one way, you combine the S1 and the T to get the identity, and you'll get S2. If you associate the other way, you combine T and S2, you'll get the identity, so you'll be left with S1. Right, then if you associate like this, this is the identity times S2, which is just S2. Also S1, if you associate like this, you get S1 identity S1. But these two things are the same, because function composition is associative. So altogether, we get that S1 equals S2. So even though we didn't make it an axiom that inverses are unique, it's actually just automatically true. It's a result. Okay, so since inverses are unique, if they exist, right? Not every map needs to have an inverse, but since inverses are unique, if they exist, or if it exists, we can talk about the inverse of T. and we notate it T inverse. Okay, so if T is invertible, then this notation means the inverse of T. Okay, so it's been like 50 minutes or so, right? Let me just state the result that we'll prove on Monday. Okay? Because you could ask now, okay, so I have the definition of an invertible linear map, but somehow this definition doesn't give me a clean criterion for determining if a map is invertible or not. Okay, also let me mention, we're in a new section here. Here, V and W can just be any vector spaces. I'm not assuming finite dimensional anymore. Okay, so this is more general than what you did in 308, because these vector spaces might be infinite dimensional. This definition still makes sense for an infinite dimensional vector space. But if I just tell you, if I give you a linear transformation in some way, you could ask, okay, how do I know if it's invertible? Do I need to actually construct an inverse? That might be difficult. So the result that we'll prove on Monday is the following very nice proposition. A linear map is invertible. It admits an inverse if and only if it is both surjective and injective. Okay, and this, I guess we didn't define in this class, but I know you learned in 300 that this is called bijective, or in 308, this is called a one-to-one correspondence. So this is a super duper clean characterization. How can you tell if a linear map is invertible? You just need to check, is the null space 0? Is it injective? And does it hit everything? Is it surjective? Then it's automatically invertible. Okay, so like I said, at the start of Monday's lecture, I will restate this theorem, and then we'll prove it. All right, well, see you on Monday.